Alright, we'll be going over the key for exam number 2 from 2014. So the first question here asks, please explain what happens in an NMR experiment. What changes with an increase in magnet strength from 45 megahertz to 300? So basically this is asking us to remember, right, in NMR we use radio waves. We align all our H's in a large magnet, either to their alpha or beta states, right? And the radio wave hits them, right? And depending on how shielded or de-shielded you feel the radio wave, right? And then you measure how it's affected. A smaller magnet is more like watching something in standard definition, so you can't see all those fine differences in different types of H's, whereas a 300 would be more like a high definition, right? So you can really see the difference between those alpha and beta states, right? So as you increase the magnet strength, the difference between the alpha and beta states also increases, and so we see more of a resolution. So this one's asking you to take a look at this structure and say what are three major fragments we should see for the following compound. So we wanted 3 different cations, right? Mass spec we see cations, so we have to see plus charges. And we want to make tertiary carbocations if we can because there's more hyperconjugation. Another thing we could also do though, so all of these would be tertiary carbocations, right? If we broke that bond, broke there, or broke any one of these 3, we'd make tertiary carbocations, but these 2 are tertiary and they're next to a pi bond, meaning there's resonance in either case, which would really spread the charge out more. So these would actually be more stable fragments than just a regular tertiary fragment. So for this one, your classic mass spec experiment, an electron beam comes in, knocks out one electron. The easiest electron to knock out is a lone pair electron in this case. We say here we want you to go draw the product twice. Here we want you to do a heterolytic cleavage, right? Show arrows in both products, and here we want to show an alpha cleavage, show arrows in both products, right? So in the first one, if we show this one, it's a alpha cleavage. So if we zoom in a little bit here, right, we see that this is the alpha carbon, that's the beta carbon. So we're going to break the bond between the alpha and the beta carbon. We essentially have the one electron come from the oxygen, one electron from the bond between the sigma bond between the alpha and the beta carbon, and the electron goes there, and that would give us this product, right? The cation, and then the methyl radical from what was the beta carbon. You could have gone the other way as well. That's fine. You could have done it that way too, and had a dot on there. It's up to you. Either way would have worked. For heterolytic cleavage, it's simply moving 2 electrons at a time. So lasso both arrows, move them over, and we get a plus charge of the carbon, and we still have the radical oxygen this time. But you make sure you show both products in this case, and the correct arrows. So for this one, the alpha cleavage, with the heterolytic cleavage you have a plus charge on a carbon, which is better than a plus charge on oxygen from alpha cleavage, but this has a full octet, whereas this doesn't, this carbocation doesn't, so you could argue either way for either one. So here, we're giving you a piece of information that says, briefly describe why the carbonyl of an ester stretches at a higher frequency in an IR spectrum than the corresponding carbonyl of an amide. Use molecules to explain your answer. First, you needed to know what an ester and an amide was, which you should know all those things by now. Now, the difference between an ester and an amide is essentially an ester has an oxygen here with a carbon, whereas an amide has a nitrogen. And once you're between oxygen and nitrogen is less electronegative, so it's more likely to do resonance, so it's more likely to donate its lone pairs. So because of that, this C double bond O has some single bond character. If you have single bond character, you're going to be able to, you'll have a lower frequency, right? Because you have that single bond character, because of resonance in this case, you have a lower frequency, right? So that means you have a lower wave number. Whereas here with an ester, oxygen is less likely to donate electrons, and is more likely to just pull away electrons. So in that case, it's going to inductively pull away electrons. It's going to shorten up this bond, which is going to make it go to higher frequency, right? So a higher wave number then. All right, for this one, for 6, it asks you which compound matches the IR spectrum below. Label the important peaks and describe how you determine the identity of the compound. Be specific. So things to look for. Remember, the peaks that are here are just as important as the peaks that are not. So if I look at this compound, I should see an OH. I look here, I do not see a big, broad OH stretch, so I can immediately eliminate that one. Skip that for a second. I see here, right, this peak, if there's a ketone that's unsaturated, that should be lower. Normally a ketone's at 1715, and it's actually lower, it should be at 1690, so I would eliminate that. This is 1740. And here I see an alkyne. I don't see any alkyne SP CHs, or do I see a CC stretch? Right, so I can eliminate this one too. So really the 1740 is indicative of an ester. Really, if you got it between these two, this was the key, but then you had to see that this was conjugated, right? And because of the resonance, because of the conjugation here, it would lower the wave number normally and be much lower than 1740. Whereas this one, induction pulls it away and makes it much higher, very similar to the question above. So this is your right answer. Alright, for number 7, the biggest thing here is list the expected multiplicities, singlet, doublet, triplet, etc. of the H's for the following compounds. Hint, not all H's are drawn. Not all H's are drawn, so you should draw those H's in. This first one, A, 2 nearest neighbors, 3 bonds away, so it'd be a triplet. B, 3 nearest neighbors, 3 bonds away, quartet. HC, now HC is getting split by HD, which is 3, but also, see these H's aren't drawn in here, these are also HD, so it's really 6 nearest neighbors plus 1 would make that a septet, and HD in this case would have 1 nearest neighbor, so a doublet, right? Again, H's aren't drawn in, have to draw in those H's. HA, there should be another peak right here, proton right here, so HA would be split by whatever this was into a doublet, and then also by B, so it would be a doublet of doublets. B should just be a doublet split by A. C should be a singlet. D should be split by E, should be a doublet, and it should be a 15 Hertz doublets because it's trans. E should also be a doublet split by that, and then F is by itself, so that should be a singlet. A here is a triplet because it has 2 nearest neighbors. B is split by A, but it's also split by C, so it's a triplet of triplets. And then C by itself is just split by B, so it'll also be a triplet. Then how many carbon NMR peaks in the last molecule above? You'd have 1, 2, 3. Let's see, 1, 2, 3, because these are the same. 4, 5, 6, 7. 7 for that one above. Again, here a little bit of matching. So match each of the following compounds with the corresponding IRs. So again, if you looked at that specific IR sheet, it gives it away here. Certainly here an OH should give it away, a strong broad peak. A ketone, a saturated ketone is 1710, according to our sheet. An unsaturated ketone is at 1690, and then again an ester, 1740. For 9, rank the following molecules from shortest to longest wavelength. So again, we're asking here, right, if it has a short wavelength, that means it doesn't have a great deal of conjugation. If it has a long wavelength, it has a great deal of conjugation, meaning it's lower energy. So we want to look for the most conjugated system here. So, looks like if this one has 1, and we count the lone pairs, 2, 3, 4 sets of electrons in a pi system. This has 1, 2, 3. This has no conjugated pi bonds, so this would take the most energy to go from pi to pi star. And this one has 2. Right? So remember the oxygen in both these cases. If it's next to a pi bond, the lone pair, the oxygen can choose to be sp2 hybridized, meaning that it can put a lone pair into a p orbital so it can be part of the pi system. It'll choose to do that. Right? So a lone pair can be part of the pi system. So 4 conjugated, 3, just 2, and 1. So longer wavelength, more conjugation. So what happens in UV experiment? UV light excites electron from pi to pi star. Alright, one of our determine the structure from the data below. First thing you have is the molecular formula. You got to figure out degrees on saturation. Here it's 6. So that should tell you first, ding, 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 benzene ring. So you should be thinking benzene ring. So that's, but you still have 2 degrees on saturation left. You got to remember that. IR here, a peak at 3015. And if it doesn't say broad, then it's probably sp2 hybridized CH. 2960 sp3 hybridized CH. 2820 and 2725. This is that aldehyde doublet, that Fermi aldehyde doublet. It's on one of your tables. 1730 tells me C double bond O. I think 1725 tells me something about what type of alkene I have. I think it tells me I have a cis alkene. Right, from the IR, so I got a lot of information from the IR. I know I have sp2 CHs, sp3 CHs. I have an aldehyde, looks like. It looks like I have a C double bond O, and it looks like I have a cis alkene. Right, so now let's go to the NMR. A peak at 9.8. That should tell me aldehyde, so now I have this aldehyde piece. I have a peak at 7.5 with 1H, 7.2, 1H, 7.1, 1H, 7.05, 1H. Right? So there's 4 of those in the aromatic region. Right? So that makes me think I have a di-substituted benzene ring. So I have 4 H's in this system, in the aromatic region. But if I look at this, it's not as symmetrical. I have 4 different types. So a lot of times we're doing where we have a symmetrical bond, so there'd be 4 types of H's in the aromatic on the benzene ring, but there's only 2 types. Here we have 4 H's, but 4 different types. So the substitution here is a little different. So this would give me 4 different types. This one should be a singlet because it has no nearest neighbors. This one would be a doublet. This would be a doublet of doublets, and this would also be a doublet. So that matches up with these. So I like this pattern here, that type of substitution. So I have an aldehyde and I have a benzene ring. So I subtract the benzene ring from the total. I subtract the aldehyde from the total. I got C8H15. Now I look at 6.35, 10 hertz, 5.0, 10 hertz. That tells me cis alkene. So I'm going to subtract that piece out. 10 hertz again is that cis alkene, which also lines up with that 725 from the IR. So I can subtract out that C2H2. The next thing I have, let's say I go back to 0.82, 9 H's. It's all a singlet. That makes me think of this tert-butyl piece. So I'm going to subtract that C4H9, right? 9 H's, all the same as singlet. Really shielded. So that makes me think of carbon with 3 methyls that are all the same on it. Subtract that piece out. Then I have a peak at 2.45, that's a triplet, and 2.39, that's a triplet, and these are 2 things coupled to each other. So I need to think of CH2s. Subtract those out. And I have my 1, 2, 3, 4, 5 pieces. Now I got to put it all together. At this point, one possible combination would be to put the tert-butyls here. I think they have to be off the alkene, the benzene, and then these H's are both at 2.4, 2.39. Should be more like allylic, so they should be next to either a carbonyl or the benzene ring, so that makes sense to put them there. And there's your aldehyde piece. Alright, for number 11, again, trying to determine the structure, but now we're actually just giving you the spectras. Some things to look at here. So let's look at the IR first. What does the IR tell us? So I would write in here broad stretch. That makes me think OH, and let's looking at this. This makes me think of carboxylic acid too. Also, I see 2 carbonyl stretches. It looks like 2 C double bond O's. So maybe I have 2 types of carbonyls. My mass spec here, they actually do give you the molecular formula, so you can figure out the degrees on saturation. So degrees on saturation was 6. So that tells me ding 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 benzene ring, which counts for 4. But then each one of if we have 2 carbonyls, that would get us to 6. So that makes sense. These are little notes I'll be writing to myself the whole time. You have a C13 in here, which is interesting. It tells us we have 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's telling us there's different types there. There's 2 peaks buried underneath there that's not resolved. So that tells us 9. There's 9 different types of carbons. I'd write that there. Now I go to my NMR. What is this telling us? Well, this looks like an OH, right? 11.0. 1 acid exchanges with D2O. That tells me that's a carboxylic acid down there. So one of my first pieces, I would say, is a carboxylic acid. Good. Carboxylic acid. What else do we have here? We have protons. Our 2 peaks in the aromatic region, both worth 2 H's, are doublets. That makes me think exactly this, that they have a di-substituted benzene ring that's symmetrical, at least, and they're both coupled to each other. So I take that piece out. Let's go back up and see the subtract. We subtract our C6H4 for our benzene ring. Let's see, we could subtract out our carboxylic acid, which we've shown we think we have. We could look back down here and say, well, we have a 3H singlet, so it's a methyl at 2.4, so that seems kind of an allylic region next to a carbonyl. It has no nearest neighbors, so I would subtract out a CH ring. I wrote no nearest neighbors there. Good. Subtract out my carboxylic acid piece. All I have left is a CHO2. So let's see, what could that be? That makes me think that I have an ester. Sorry about that. This is subtracting out the ester I believe I have based on the 1766, and this is actually subtracting out the carboxylic acid. So at this point, I have a CH3 that I'm presumably going to have to probably put next to the ester here. So I have a ester, a carboxylic acid in this. There's only one way you can go on. And I have either sides of the benzene ring that I can check. Everything should check out. And let's see if we have 9 carbons. Maybe we should have 9 types of carbons from this. 1, 2. We should have 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all different 9 different carbons. Good. Alright, for this last bonus one, first do your degrees on saturation. From this, you get 2, so no benzene rings, 2 pi bonds or rings. Have only sp3 hybridized CHs. To have 2 stretches overlapping at 1746, that's straight up in the ester region, so that tells me I have 2 esters, 2 different types. I have 1, 2, 3, 4, 5, 6 different types of carbons, so 6 different types of carbons. In the NMR part here, it says I have 2 degrees on saturation. If I look at, let's see, this CH3 right here, this tells me CH3 right next to a carbonyl, like the allylic region. This CH3 tells me something a CH3 next to an oxygen. An expansion right here shows a doublet with 3 H's. That means it's CH3 next to 1H. Right, turns to doublet. And then I have another expansion right here for this 1H, which is a quartet, means need next to be next to a CH3. So that's right there. And now I know I have 2 esters, so I have 2 esters in. Subtract all these pieces out. Now I got to put them all together. This CH3 needs to be next to an oxygen. This one needs to be next to the other side. And then obviously you put these other 2 pieces there. So you have one CH3 next to the oxygen there. The other CH3 on the opposite side. So 2 different types of esters. You need quartet. And then you get your final answer.